that is Hamilton principle. Hamilton principle, but now not for a holonomic constraint, but for a semi-holonomic constraint. For semi-holonomic constraint. Okay. So that is the today topic. Okay. It is also defined as the Lagrangian multiplier method. Okay. So the other name is you may say that the Lagrangian multiplier method. Okay. So the change is only that if there is if the constraints are not holonomic, then what will be happen? If the constraints are non-holonomic, you know that I should say or not, I don't know. Up till yet, we don't know how we can solve the and what will be the solution, how we will describe the system for non-holonomic constraints. Okay, maybe some has done some type of the calculation, but I don't know. I am not aware about that. But even I have not done such calculations. So I don't know anybody has done any calculations if the constraints are non-holonomic and how he reduce the number of parameters and what he has done and what type of the calculation. I don't know about that. Okay, maybe in YouTube someone watching this lecture and may they have calculated, they may be shared with them. As we have described the last lecture. In last lecture, we have stated the Hamilton principle for holonomic constraint. In holonomic constraint, according to Hamilton principle, we have taken that the action will be globally stationary. But someone is telling me that he has done the calculation, or he is doing calculation. If that is locally stationary, what will be happen and why that is not okay. So if I done it or I receive this calculation, I will be shared with you. Okay. So I will be waiting for a response. Hopefully, if he shared that, I will be shared with you, and I will try to. Okay. So our new time. So not. So this lecture is not about the non-holonomic, but this lecture is about the semi-holonomic constraints. And this semi-holonomic constraints we also use in the BS undergraduate level as well as the advanced level classical mechanics or graduate level classical mechanics, where the position and velocity don't commute and they are connecting with the some constraints. Okay. But that is out of the scope of your course. Your course is about the undergraduate level. Okay. According to undergraduate level course, as we know that what is the Hamilton principle? We know that Hamilton principle is the actions must be globally stationary. Okay. Or you may say that the action, action that is the line integral of Lagrangian, that is the function of q and q1 dt, and that must be the variation in that. Okay, the variation in line integral of Lagrangian must be 0. Why that is 0, I have already explained in my previous lecture. Okay. Okay, if this is 0 and we get Euler Lagrangian, but if this is too far for holonomic constant. But what's happened if the constraints are not holonomic but semi-holonomic constraint? We know that what is the meaning of the semi-holonomic constraint. Semi-holonomic constraint means the constraint is not only function. Holonomic constraint means the constraint is You know that holonomic constraint means if the constraint is like that Fm is equal to Q is the function of, mean constraint is function of weakly zero. That constraint is the function of position only. Yes, for holonomic constraint. But if that is not a holonomic constraint, then what will be? That is the semi-holonomic. But for semi-holonomic constraint, for semi hollow. Okay, firstly, I must write what is the meaning of. If holonomic constraint, we can get the generalized coordinate and generalized coordinate as a good coordinate, and all coordinates will be an independent form. Mean if you have two different Q's, mean QL and QM, if we take the dot product, that will be independent from each other. Mean if they are the same, we will get the square of the magnitude. If they are different, then that will be a zero. I have already explained each and everything in my previous lecture. Okay, so for holonomic constraint, that will be a good coordinate. You may get a good coordinate. Okay, they may be a spherical coordinate, they may be a Cartesian coordinate, whatever the good coordinate. So if that are a good coordinate, it may mean for a holonomic constraint, you reduce the degree of freedom in such a way that finally you will get the independent coordinate. And as you have learned from linear algebra from me, and I have also explained, and this theorem, we have also discussed this theorem linear algebra course, that if you have a number of independent parameters, then you may reduce the degree of freedom to get the independent coordinate. That is the references in my lectures on the linear algebra course. That is the theorem, if you remember that. Okay. Each and everything is discussed. But for but it is true only for the holonomic constraint. But if that is the semi-holonomic constraint, then you can't get the good coordinate. And virtual work will be not zero. Okay. But for semi-holonomic constraint, what will be happen for semi-holonomic constraint? If we consider that that is the function of position, velocity, or time. It may be our time or position and velocity only. Okay, but we consider that is time, and that is weakly equal to zero. Weakly means derivative may not equal to zero, but they are itself are zero. Okay, and we know that partial derivative if some constraints are equal to zero, it is possible their partial derivative may not equal to zero because they are starting depending upon each other due to the constraint. But actually, I think it will always happen. I mean, if something is connected with the constraint, they will start depending upon each other. Okay, so I must write. Okay, if you one thing, I must write in the form of RLM. Because these are not generalized. If they are generalized, they must be independent. I think it is my mistake. I must not mention it as a generalized coordinate. It must be a conventional coordinate, because if the general coordinate, if they are a generalized coordinate, they will be independent. Okay, so I must write R square, and remaining is the same. And this is the true for. The same will be true for this. Okay. I think I explain it that Q will be not correct. Why Q can, because usually we Q reference as the good coordinate and generalized coordinate. If things are independent, if they are not connected with the constraints, if they are a good coordinate, then Q will be defined. But for holonomic constraint, I think Q, I don't think Q should be mentioned. Anyway, if you write Okay. So if I write in the form of this R and R dot, okay, dt. Mostly books write in the form of Q. I will consider why they are right. I will try to understand why they are writing the Q and Q dot. I think I should not write Q and Q dot because Q and Q dot usually represent the good code. No. Please. Okay. Yes, but for holonomic constraint, they were equal to 0 and good coordinate will be not defined. Okay, because they will, good coordinate mean independent. So mean the R, L and R, M that that can't be right as the independent. They will be not independent. Okay. Since they will be not independent, okay, then if they are not independent, then virtual work done by constraint force will be not disappeared. Okay, as we have done in this case of the holonomic constraint, the virtual work done by the constraint will be. Okay, this question will also come in the exams. Always remember the constraint itself is not 0. I mean, mostly people write that the total force of the constraint will be 0. Net force of the constraint will not 0, but their work will be 0 for holonomic constraint. But for non-holonomic constraint, even you can't, because you can't define the good coordinate, you can't find the good coordinate, so you can't ignore the effect of the constraints. Okay, so in this case, the constraint force will be appeared. Okay, so net virtual work done by constraint will not be disappeared. So this will not disappear. Okay? No, I have already explained for Lagrangian. The condition is only that that must be that will be a scalar quantity. Okay, and that must be a scalar quantity, and that must be a function of position and velocity, not a momentum. Okay. The other thing is that you are right. For Euler-Lagrangian equation, the Euler-Lagrangian is be written only on the basis of the generalized coordinate. You are absolutely right. Okay, but here that will be not Euler. We will prove that that will be not a Euler-Lagrangian equation, but that will be different equations. Okay, and there will be a constraint force will be involved there. Okay. Okay, that's why for holonomic constraint virtual work 0. That's why that will be a Euler-Lagrangian equation. Okay, Euler-Lagrangian equation. Okay. But now the result will be not Euler-Lagrangian equation. Okay, try to switch off your mobile. Okay, so okay, next. So they will be not independent. Good coordinate can't be defined on for that. For semi note kar. Okay, good coordinates can't be defined for semi-holonomic constraint. Okay. Okay. These are the number of m is the number of the semi-holonomic constraints. Okay. If phi 1 is 1 constraint, phi 2 is 2 constraint, if phi 3 is 3 constraint, if phi 1 is 0, phi 2 is 0, phi 3 is 0, phi m is 0, then their linear combination will be also a 0. Okay, mean you may say that the C1 phi 1 R into R plus C2 phi 2 r into r1 plus and so on. Okay, that will be equal to all is 0. This is 0, 0. So this will be net result will be a 0. Weekly 0, not actual 0. That will be weekly 0. I have already explained what is the meaning of weekly 0. Weekly 0 means their partial derivative is not 0, but they are itself is 0. Okay. If they are a weekly 0, then what will be happen? So I have roughly written it to explain only. Okay. But you know that we use the dummy indices. Dummy means there is a summation that is understood. So I may write it in the form of that will be equal to 0. Okay. If I say this is equation 1 and if I say this is equation 2, okay. By combining 1 and 2, okay, may I remove it? Okay. If I combine 1 and 2, what will be happen? One and 2. I may write as actually this Lagrangian, the line integral of Lagrangian is not 0, but their linear combination actually the action is not only the Lagrangian for semi-holonomic constraint, that will be the Lagrangian, and in this Lagrangian there will be a combination of linear combination of semi-holonomic. Okay, jagah? Okay, yes. Actually, I'm habitual to write as I have stated in last time, we will write that 30, not. Okay. So this will be now this is this is equal to 0. Okay. So this linear combination is equal to 0. This is your Hamilton principle for semi-holonomic. Okay. Munib. Okay. Shahriyar. Okay. Shahriyar. Okay. Yes. Okay. So now this will be a so this will be the Hamilton principle. Okay. So that will be changed. Okay. Yes, that is also a weekly 0. Okay. You are right. Okay. I think I must write here. So finally, what is the Hamilton principle? Hamilton principle is that this action, which is not only the line integral of Lagrangian, but it will be T naught to T L R into R dot. R is not into, not multiplication. L is function of R and R dot plus Cm phi m R into R dot that is equal to 0. So This is Hamilton. Now this is the Hamilton principle for a semi-holonomic constant. Okay. This is Hamilton principle. Weakly zero. Okay. This is Hamilton. Okay. So this integration is actually the double integration. One is applying on this, one is applying on this, and this C may be function of T. Okay, if that is function of R and R dot, this constant, this linear combination may be up. That must be independent from the R and R dot, so they may be function of T. Okay, so I must write in this way. CM T function of T. Okay. Okay, so that has two parts. That is one, and that is the two part, because there is a linear combination. We solve it. Okay, you must remember that the independently they are not equal to 0. Their combination is equal to 0. Okay.
So, is CM the constant?
CM constant with respect to R and R dot. Yeah, we usually use this type of terminology in the differential equation. Constant means the independent from the variable which are using in the differential equation. That doesn't mean कि वो हमेशा constant होगा. Constant means that will be constant with respect to R and R dot. Okay. Okay, got it. If your constraint is function of, as we have taken the examples of the semi-holonomic constraint, the ball is rolling on the inclined plane. In that case, the semi-holonomic constraint is the function of velocity. Then C may be a function of R2. Means that that must be independent from these variables. That is not necessary. That must be independent from each and every variable. Okay. Now it's clear. Okay. So. So it has a two terms that are adding. Okay. So for simplification, we consider the first term and then second term. Okay. CM. T is a function, not superscript, not subscript. C is function of, as constraint is function of position and velocity. Lagrangian is function of. Yes, you must try. Okay. Okay. Let's consider. First term. T naught to T L function of R and R dot dt. And we have already proved that this this will give you not equal to 0. This is not equal to 0. I'm not saying that is equal to 0 as we have done in the last time. But solution of this differential equation we have already find that is and that is in last time last time this will be multiply with the dt or delta q. Yes. Last time we have this will be, this is the this result. Last time we approved this equal to not equal. We have proved that that is 0, but in this case this is not 0, so that it will be not 0. In last time that was 0, but here it is not equal to 0. Okay, this is not equal to 0. You must keep in mind. Last time that is equal to 0 because that term was 0, but this integration was this equal to this. Okay, because it is not equal to 0, that's why this will be not equal to 0. Okay, so but the 1 will be equal to this. Okay, they're very simple. And now consider 2. That is the T1 or T0 to T CMT phi M R into RM oh sorry, not equal to this. This is the integration. Not equal to this. This is an integration. Okay. We may say that this is complete function as let's suppose xi. Okay, let's suppose, and this is a function of r dot and t. Okay. And Lagrangian is also function of position, velocity, and time. Okay. As L is function of r dot and t. So the difference of the function, that may be a sine, cos, whatever. Only difference is the function. The remaining is the same. So answer will be same. So we have not to do any calculation again. Okay. So we will simply put. We will get this. We put this term instead of this L, and that will be the result. Analogous. Okay. So we have not to do the repeated this step. Neither not in this step because we have already done, nor we have to need to calculate again here. Okay. But we may use the reference only. Okay. So that's why I'm saying that today's lecture may be a small test. Okay. So you will get T naught to T d by partial CMT phi M R into R dot over R dot K, yes, minus partial CM phi M R into R dot over R K delta Q K not equal to, not equal to 0. This is also not equal to 0. Okay. T. Everything will be same as this. Only L will be replaced with the this term. Okay. Everything is the same. Okay. Xi. Yeah, I have used, okay, if you are confusing with this, you may use alpha, whatever you are interested. I was interested in xi, so that is up to you. What is your favorite alphabetic, okay? You may use in the exams, okay? That's up to you. You are liberal, free to use. Okay. This is R. This is function of T. Okay. T. The product formula will be not applied because, as you stated, okay, because C is constant with respect to R, so it will become out from this partial derivative. But here C is function of time. Here is time. C is constant with respect to R dot, but it is not constant with respect to time. So that will not come out from the sign of integration, but it will come out from the. To explain this, I may write in directly, but for you I will write in some steps, okay? Because if to save my time, I leave some steps. Okay? I will avoid. If I will avoid some steps, I know that I have to repeat and I have to waste my more time. So that's why I'm not interested to take such kind of risk. Okay. So for you, I will. Do these easy steps too, okay? I'm again writing again and again that is not equal to 0 because you must not confuse it with the previous steps. Okay. So now the product formula will be applied. Okay. The remaining is the same. Okay. But here the product formula, if this is A and this is a B, you will apply the product formula because the two terms are multiplying. So yes, R K, okay. Okay. So product formula will be applied. What is that? T naught to T, the derivative of first. Okay. Second as it. Okay. Plus first as it. I have already explained many and many times the time derivative and R velocity derivative independent, so they may interchange because it is a partial derivative, and so we may interchange. So it will become in that we have done these exercises many and many times, even driving the Atta-ul-Latif equation from the generalized coordinate. So that's why I will not repeat, and I will save this step. Okay. So CM, and this will become partial phi m dot R into R dot Okay, this change with, okay, the first element as it, the derivative of second with respect to time, so that will become a total derivative, that is total derivative. Okay. So that will become a dot, okay, and minus Cm that is not equal to, oh sorry, if I say this is 1, okay, this is 1, the 1, okay, yeah, this is 1, okay, and this is solution of the second part, okay, 2, and if I say this is equation x, okay, so this all 1 and 2 will be, 1 will be put here and 2 will be put here, okay, and so this will be result, okay, so, yes, you are right, I was wrong, sorry, you are right, this is 1, yes, you are right, this is not 1, okay, yes, sorry, this is not 1, मेरा ख्याल है सर मेरी वजह से चुप कर गई हैं ठीक है ऐसे you are right okay it was the second solution yes right this is this is okay yes now it's true okay so both have this common, okay, and if I want to save my time, okay, क्या किधर अच्छा ओ यार इतना बड़ा मसला नहीं था अच्छा ठीक Thanks for question. Acha, what raised a typing mistake. Dr. Bilal Masood from CHEP always stated that there is a typing mistake. मैं अक्सर ऐसे करता हूँ वो कहते थे there is some typing mistake. Okay. He is my one of the best, my favorite teacher, Dr. Bilal Masood, the chairman of Center for High Energy Physics. Dr. Dr. Mahmoodul Hassan, Dr. Mahmoodul Hassan, chairman of the, that is the my supervisor in my MPhil thesis, Dr. Mahmoodul Hassan. That is the he is the chairman of the physics department, and Dr. Amir Iqbal, the string theorist, and he is graduated from the MIT, and he was the assistant professor in Washington University. So he is my boss and my colleague in the Lums University, and I have learned many things from him. He is a very genius person, and you know that he is not presently, unfortunately, due to some circumstances in Pakistan. He is not in Pakistan. Okay? Yes, you are right. So he is my colleague and my boss, and you may say that he is my teacher too, because during when subordinate, I have worked under him, then I have learned many things. Dr. Faisal Akram is also, I'm very grateful with Dr. Faisal Akram from the CHEP. And so they are one is my my FSc or BSc teachers, that is I must mention, the name is Gul Shah. Okay, so he from Sargoda University. Okay, he was the great mathematician. In FSc and BSc, he helped me to understand many things. Dr. Gul Shah. Well, not doctor, he was not doctor, but he Gul Shah Sahab. And in metric, Dr. Nasar Bhatt Sahab, he is a good mathematician in mathematics. He was Nasar Bhatt Sahab. Punjab University. Okay. In in National Center for Physics, I'm really grateful for Dr. Munir Rashid. Okay, he was a great mathematician. Now, presently, he is in Australia. Okay, and if I am saying different names, the one that's the most important name, that is the Pal Chandre. From India. I don't know the name of his university. He comes in at the 12th regional conference, and now I'm in this position only due to him, because when I was doing work on the non-commutative geometry in quantum field theory, that was a very difficult to understand how we should do, what I should do. That only the person in this earth, that was I must mention, I always grateful, and I always talk about him, because I am really, really grateful and thankful for the Pal Chandre. From the American, he comes the American university. By birth he was Indian. The Babar Qureshi, I don't know. I think he is in Karachi. Babar Qureshi. He was the student of the Bal Chandre, and Bal Chandre, I can never forget him, because he was the only person. He helped me to understand the non-commutative geometry in quantum. He gave me only the 5 minutes. I think not more than 5 minutes. Okay, only the 5 minutes. He helped me to understand how I must find the papers, what type of the papers, and how I must continue my research. Okay, so I'm really grateful, and I really miss him. Okay. I think that's the discussion after completing this lecture. Okay, that's the part of the after completion. So I think no, that's why I'm saying firstly we have to complete on this. Okay. Because that is the topic of the after this, okay, after completing this topic, okay. So and sorry, I was wrong. Actually, the position. Okay, it's not a fact. Okay, what we write first or what we write second? I think I'm doing wrong, because it is not equal to 0. Okay, so I think when I proved there was a plus and here was a minus. If you remember, I think in last lecture. Minus and then we multiply with the minus, because there was 0, but now there is no 0, so we can't do it, and that is not equal to 0. In last lecture there was a minus, there was a plus, yes, and that was equal to 0. That's why we have multiplied it with the minus 1 and this plus, and that becomes. So I think actually there is a mistake. That must be minus term and that must be a plus. T not T. Please correct it. Okay. And so the plus term will be minus and minus term will be plus. Okay. Yes, so Smith. Yes. And similarly in this way, now this become a 0. And here is also plus was partial L over partial R. This was a plus term, okay. Only the sign will be changed, okay. Plus, minus partial L over partial R dot, okay. You must write close to this. Okay. That was, I think, yes? Yes. Now this is equal to 0. Okay? Okay. Now, okay. I have added that term. This. Okay. 1 and 2. If this is weakly 0. Open not equal to 0. Not equal to 0. Actually, there is no condition for not equal to 0. There is a condition is only for the equal to 0. Okay. So this will be the result. Even if you write that is weakly not equal to weakly 0, that is also acceptable. Okay. Because you may understand after that, because when you make a equal to 0, that will be a weakly 0. Okay. If you write that is weakly 0, then it is accepted. If you write not equal to 0, then it is accepted. Because for weakly 0, there is no condition. Okay. Not 0 can be कोई condition. This is not 0. This is not 0. But their linear combination is equal to 0. Okay. So if we add 1 and 2, this will be the result. Okay. And this will be equal to 0. क्या? Weakly 0. I have write a weakly 0. Yes. Weakly 0. Okay. As we have already discussed, this term, total term, this large term, totally equal to 0 for all the integration, or globally 0. If the term is completely 0 for all values of, there is no, I have not mentioned any condition on T or R. If that is equal to 0 for all the terms, then integrand will be 0. Okay. Here okay, I write it. Z. Since integration is not mentioned. It's not is weakly 0 for arbitrary. There is no condition on that. For arbitrary RK and T. So since integration is weakly 0 for arbitrary RK delta T, you have not specified what kind of the RK and for what kind of RK is 0, what kind of RK is not 0, but it is 0 for everything. Okay. So it means its integrand will be 0. Okay. This implies that integrand will be 0. Okay. If this integrand will be 0, this term become a weakly 0. Now we can change the sign. Okay, that is 0, so we may change the sign. So minus if you multiply minus with the minus, then this term become a minus, this plus, and this become a negative. Okay. And next line. It must be understood that it is a new line, but I have taken the advantage that I am using the whiteboard. But in notes it is not possible. Yes, I agree. But you may take the advantage. You can read note or rewrite after the completing lectures, because it is also available on the online available, freely available. Okay. So as you now, how we may remembered it, because हमें ये question याद भी करनी है और इसे we have to utilize it. So what is the trick to remember it? Okay, because the derivation of this equation is very simple, but to remember this it is a difficult. Okay, so I must write in this way. I usually write in this way that so that I can remember it. This is as we know that this is Atta-ul-Lagrangian equation. Let's take it, but it is not equal to 0, but it is equal to here is plus. When it moves towards the left, it will become a minus. Okay. This term is plus. This term is plus. When they move toward the right, they will become a minus. So okay. Minus Cm partial phi r partial phi. Phi is the function of r k dot. I must no sorry. Okay, if I take minus Cm phi dot phi, I must r phi dot d r dot k. Okay, plus Cm phi m r phi dot r dot k. Yes, minus Cm, we take Cm as a common, minus Cm partial phi over partial r k, that is equal to 0. So this is defined as Lagrangian multiplier. Okay, here Cm is the constraint. It will give you the information about the constraint. Okay, and you can find the constraint force. Cm will be the constraint force. So if you are interested to find, if in some exercise, if the constraint forces are important to find, then you may find the constraint force by using this Atta-ul-Lagrangian multiplier method or Hamilton's principle for a semi-holonomic constraint. Okay, so this will be, I think it now it is very easy to remember. Yes. Okay. Anyway, you have to remember it. But what is the way to remember? It depends upon you. So no term will be. There will be no free indices else k, and you may see that there is no free indices. Okay. I think it's complete. Yes. Okay. For the today it is enough. I think. Okay. Where? Here? इधर Now it's okay? I think no, it must be okay. Okay, thanks.